Okay, today we're going to be reviewing Chapter 1 in the Green Book. So this is our Green Book Chapter 1 review. You got a test coming up soon, or if you're just starting the unit, either way, this can help you get started. We're going to be working on representing rational numbers on a number line. Most of you should already know what a number line is just from past years, so we're not going to show the number line at this point, but let's get some of the vocab that we need to know that's within this chapter. So as you see, we have integers. And integers is just, it has to be a whole number. Positive or negative doesn't matter. So -3, let's just give some examples. I could have -3. I could have 7. I could have 1 0 0 2 3 6. So 100,236. It wouldn't matter. Okay, absolute value. Absolute value is our distance a number is from 0. So if I say the absolute value of 3, absolute value of -3, or 3. They're all 3 away from 0. We'll get into more on what absolute value is in just a few minutes. But we continue to say absolute value of a positive number or fraction is itself. Absolute value of a negative number or fraction is its positive form. Don't worry about that, but that's a good little thing to look at. It'll help you as we continue on. Okay, so let's take a look at the number lines. Hopefully we recognize this. As we said, you've been using this since you were young. We're just adding in the negative numbers now for you. So we have -1/2, -1. If we look at -2 and we look at 2 on this number line and we check out where 0 is, and we wanted to measure the both of these, I should be able to see that that is the same exact distance as that is. And that is why we would say that the absolute value of -2 equals 2, because it is 2 places from that 0 on the number line. Okay, here it is looking at it a little better. I really like this little picture here, but absolute value, which we've said over and over again, is the distance the point is from 0. Okay, so up here at the beginning, -4 equals, the absolute value of -4 equals 4. And just to clarify, to make sure that we know what this is, whenever I have the bars like this with any kind of number in it, that refers to the absolute value of that number. So the absolute value of -3 is 3. The absolute value of 2/5 is still 2/5, because as we keep saying, the distance from the point to 0, that is what we're dealing with absolute value. So if we look over here, -4 equals 4, well, we check out the 4, and we see that is 4 units from 0. Over on this side, I have the absolute value of 5 equals 5. So I find the number 5, and I see that that is 5 units from 0. Okay, let's take a look at these down at the bottom. What is the absolute value of the following numbers? If I want to know the absolute value of 2/3, I can look at that as the absolute value of 2/3, and that'll equal 2/3. If I want to see what the absolute value of -1/4 is, then that would be 1/4. So once again, it's just its distance from 0. So if we look at the other two, the absolute value of 4, that should be 4. The absolute value of -4, let's all think for a second. Very good, that is 4. And our last one, E, the absolute value of -3 3/4 is we just get rid of the negative, and it's 3 3/4. We're just looking at what is its distance from 0. Irrational numbers. We need to know the difference between a rational and an irrational number. So first we'll take a look at the 4 basic categories that we're going to consider rational numbers, and then we'll take a look at 2 of the most common ones that we look at that are not rational. But if you want the technical definition of a rational number, we say that it's any number that can be expressed in the form of m/n, where m and n are not 0. Okay? So we don't want this to be expressed with zeros, especially the n. We don't want a 0 in our n, which means that it would be a number that could not happen. Okay? So examples of rational numbers, whole numbers, 5, but it could also be 3, 7, 2, -5. It won't matter. Any of those are whole numbers. So positive or negative, so we'll say integers. Okay, on B, fractions. So if it's expressed as a fraction using whole numbers, we know we're going to be good. So here I used -3/4. It could be 5/8. And whatever you want to use. If it's a fraction, it is a rational number. Repeating decimals. So if I had 0.2344444, so I know those 4s are repeating forever. It's rational. If we'll get out to the point that it will repeat, then it's rational. Our last one, terminating decimals. So we think of anything that terminates. It stops. It ends. So a terminating decimal. So if I have the number 2.3, well, it stopped at 3. It went in perfectly. It is done. We consider that a terminating decimal. Our example, we had negative 2.45. So if I look at that terminating decimal of negative 2.45, it ended at the 5. It did not continue. It was done. So if we think, we have patterns in A, B, C, and D. A, a whole number, it ends. It ends at the whole number. B, it's a fraction. So it's expressed with 2 whole numbers. C, repeating decimals. So I have a pattern that goes on. It repeats the same pattern forever. And D, with terminating decimals, it stops. It ends. Well, our numbers that are not rational, or we call them irrational, those do not have patterns. They just go on any way they want. They're always random. The best example of this is pi. So the symbol pi, and typically you always see it written as 3.14. That's what you're taught young. But then you start to see that that number will go on and on and on. I've had some students that can rattle out to 100 decimal points what pi is, but they can never get it fully exact because it never ends. Pi is a never-ending number, so we say pi is irrational. Irrational. Okay. Now, we've been working with our perfect squares. Well, a non-perfect square, so if I say the square root of 7, the square root of 21, I could also say this not just with square roots, but cube roots, any other kind of roots that are not perfect. So if I said the cube root of 10, all of those will end up with decimals that repeat on forever that do not work. Okay, now we want to learn how to write rational numbers as decimals. So I have this rational numbers, I have these fractions, 1/4. Well, my first step always to any of these is going to be I divide the denominator into the numerator. So in this case, I will take 4, which is my denominator, and I will divide it into my numerator. So I go 4 divided into 1. Well, that doesn't work, so I'll put a decimal point on the top and bottom, add a 0. And how many times does 4 go into 10? We should know that is twice. 4 times 2 is 8. I have 2 left over. Let's put another 0 here, because we want to make this either repeat or terminate. If it's going to be a rational number, it will either repeat or terminate. So now 4 into 20, that goes 5 times. 20, 0 left over. That ended, that terminated, and that is why we have a 0.25. Okay, I'm going to actually change this 3/5 to 2/3 because it'll act a little bit different for us. So in this case, I'll go denominator into numerator. So I'll go 3 divided into 2. Once again, that doesn't fit. Let's put our decimal in, add a 0. 3 goes into 20. Okay, that goes in 6 times. 6 times 3 is 18. I'll take my 2 down below. Add a 0. 3 goes into 20. That goes in 6 times. I will have 2 left over. Okay, so if we look at this pattern here, I have exactly the same number both times. I had a 6 and a 6. If you look at what I have left over at the bottom, once I divided 3 into 20, I had 18, I have 2 left over. That is the same pattern every time. No matter what, it will go on forever. 0.6666666. I can also write this simply as 0.6 with a line over the 6, or I could call that 0.6666. I could put any number of 6s I wanted and just put dot, dot, dots to make sure that you know that it will continue on forever. I'll let you try 3/8 on your own, but that's another one we could do. We will divide the denominator into the numerator. Just always remember that part. Rational numbers is repeating decimals. Let's go ahead. Oh, I jumped ahead on my last one, and I'm sorry about that when I added in a repeating decimal before, but let's go ahead and look at this. Denominator into numerator. So 11, which is my denominator, into my numerator, which is 3. put our decimals up, put our 0, and I see that will go in twice. 2 times 11, 22. I have 8 left. Let's drop a 0. 11 into 80. 11 into 80. How many times, everyone? Okay, good. That'll be 7. So we'll have 77 with 3 left over. Ooh, look at something that we might notice. See if any of you have noticed something. But 11 goes into 30. How many times? Well, that'll be twice. 2 times 11, 22. I have 8 left over. 80. I've got a 7. Hopefully you're recognizing right now that we have the pattern of 0.2727272727. So the best way to write this is 0.27 with a bar over it, or 0.27, whoops, 27 ... just so I know that that will continue. Okay, on the next one, B, 13 twelfths. If I'm going to divide, I'd much rather make this easier numbers to divide with. So I'm going to say that 13 twelfths is the same as 1 and 1 twelfth. Because if I take away 12 twelfths from 13 twelfths, I have 1 twelfth left. And 12 twelfths is equal to 1. This makes life a lot easier because I can go now 12 divided into 1 instead of dealing with a 13. We drop a 0. Ooh, that will never go in. Drop another 0. 12 into 100. We will go 8. 8 times 12 is 96. We've got our 40 left over. 12 into 40. Oops, sorry, I had to drop my 0. Forgot to do that. We'll have a 3. That will be 36. I will have a 4. Ooh, we're starting to notice a pattern here. I had a 4, I had a 4, so I'll notice that this 3 would go on forever. So my final answer to this, and I got to add my 1 back in, is 1.083, and only the 3 repeats, so my bar will go over the 3. Compare rational numbers. Here's where I just want to do the math on both of them, see which one's bigger, which one's smaller. So I have 2/3. If I do the math out, I will end up getting 0.6666 or 0.6 with a bar. If I do 3/4, I will end up getting 0.75. You can go ahead and do the math on those. I'm just trying to speed up for you. And the way that I'll express that, then I notice that 3/4 is larger than 2/3. So if I was to write this, I'd say 2/3 is less than 3/4. Over on the other side, I need to remember the bigger the negative number, the smaller it is. Or the smaller the negative number, the closer it is to 0, so it's actually larger. So let's take a look at these. If I go -1/4, if I do out the math, I'm going to get let's redo that, -0.25. If I do -2/7, if you divide the denominator into the numerator on that one, I will end up getting -0.286. Okay? If I look at that, I will see that -0.286 is further from 0 than -0.25, meaning that -0.25 is the larger number. So I'll say that -1/4 is greater than -2/7. Okay, perfect squares and perfect cubes. These are numbers that have a set of numbers that can multiply by themselves to come up with what was in the square. So examples of this, and with our classes we go through this a lot, but let's make sure we know that the square root of 1 works because that is 1 times 1. We know the square root of 4 works because that is 2 times 2. The square root of 9 works because that is 3 times 3. The square root of 16 works because that is 4 times 4. And we really want to know all of our perfect squares. Okay, I'd say up through 20 is an important number to know. On the perfect cube side, works the same exact way, and I've asked you to know this up through 10. So if I say the cube root of 1 is 1, the cube root of 8 is 2, the cube root of 27 is 3, and so on all the way up through. So we do need to know these numbers here. Very, very helpful for us.